session with the talk by Daniel Paulin, who is local. He's going to talk to us about unbiased kinetic Langevin Monte Carlo with inexact gradients.
Thank you very much. Thank you very much for the opportunity. This is joint work with Il, sitting over there, and Dan Lemkuller, who's
Not sitting.
not sitting over anywhere here. So I think it's fortunate that this comes after Julia's talk, because it's sort of similar in idea, and it's going to be just as simple as as Alexis thought. So so I'm gonna start with some brief introduction about discretization schemes, like numerical discretization schemes and splitting schemes. Then I'm going to talk about unbiased MCMC. Then I introduce our U-boo-boo algorithm, and
Sounds great.
then there's some theoretical results and numerical experiments. So let's get it. So sampling from sampling from high-dimensional probability distributions is important. Okay, I think I don't need to dwell on this for too long. And there is often getting a sample from a target is intractable, so you have to use some sort of Monte Carlo methods, such as Markov chain Monte Carlo. So yeah, I realize this is an SMC workshop, so but there will be a little bit of filtering towards the end in the applications. But most of this work is towards the MCMC area. So now, if you can create a Markov chain that keeps the exact targeting variant, then you have all this nice theory with central limit theorem, etc. Now, of course, the efficiency of this depends on the Markov chain that you choose. There have been a popular way of creating such Markov chains is by finding a continuous time process that SDE that keeps the target invariant, and then discretizing it and maybe applying some correction steps. So the most well-known is Hamiltonian Monte Carlo. Randomizing the number of integration steps is also a good idea. So then there's overdamped Langevin that's been studied before, and there's this kinetic or underdamped Langevin dynamics. So we're gonna see the formula soon, but I think most of you have seen this type of dynamics. And other popular methods include the bouncy particle sampler and the zigzag process. So in this case, you can simulate the continuous dynamics exactly. All right, so we're gonna be focusing on this particular SDE called the kinetic Langevin dynamics, where the state space is extended to include not just the variable that we care about, but also a variable that's the velocity. And you have like the first two parts are just the Hamiltonian dynamics, but you also add some friction and additional noise. So together they converge to a target distribution proportional to exponential minus u in the first component x and the standard Gaussian in the component v. So this has been studied, for example, starting from a first paper by Einstein for understanding the movement of molecules in a solution, and it's been popular in molecular dynamics for modeling evolution of molecular systems. Now, from efficiency point of view, it does have an advantage compared to not extending the space and just considering the overdamped Langevin dynamics when dxt is minus grad u xt dt plus d square root of 2 dwt. So that is the overdamped. Compared to that, usually introducing this additional variable velocity and moving in the same direction leads to better behavior for poorly conditioned distributions. So there's many papers on this. So now, assuming that you have a strongly convex potential, so the Hessian is lower bounded by a positive constant times the identity. It's been shown that the variance of this average can be upper bounded by this particular bound. So the optimal choice of the friction is square root of small m. And in this case, you have a bound on the empirical average in stationarity of this form, which is interestingly independent of the dimension. So there's no inherent dimension dependency in the performance of such methods in continuous time, okay? And if you have, especially when you look at Lipschitz functions, because for Lipschitz functions, by the Poincare inequality, this variance itself is dimension independent. Okay, so great, but that's not usually the situation we see in practice when you discretize this type of dynamics. So now we're gonna move on to discretizations, and they're gonna be interesting names that pop up. So there's the Euler-Majorana scheme. Then, okay, there's a Bau of bubble and Oabau. There's a stochastic Euler scheme, SES. Then, okay, there's other variants, SPV, SVV, BBK, and then our favorite is the UBU or BUB scheme. So they have been proposed in these papers, first in Zapatero's thesis and the thesis paper by Costas and Jesus. So the simplest thing you could do is the Euler-Majorana scheme. You just add h times the time derivative at the current position, and that's it. But as we have seen in the previous talk by Alex, this scheme typically has like strong order that's not too large in the sense of the square root of the variance. The strong order of this scheme is just 1/2. Now, sorry, no. It is 1 for this particular SD, so it would be 1/2 for a general SD, but for the kinetic Langevin, it is 1. Now, however, we can do better. So the idea of splitting schemes is that you divide this SDE into different parts that can be integrated exactly on their own, and then just go through them one by one in some sort of order. And depending on the order you go through them, you combine the letters together and create a name. And then this additional secret that if you have the same letter twice or multiple times, then you just have to apply half of the time step with those to get everything to the same amount of time in the end. So this is the way the Bau splitting works. So, and this can be integrated exactly. So, for example, for the B, the idea is that if you just consider this, then X is actually fixed. So X is fixed because X is not on the same color as this. So it will be just the same, and you just have to move along the constant velocity. So constant gradient. All right. So the advantage of this method, if you combine them in this order, is that it has weak order 2, but it has strong order 1. So what we gonna be using is this more recently proposed method called UBU. So you combine all of the linear terms together into one. It's called a U part, and the other part is the gradient U, which is the B part. So this can be integrated together, but the formula is too horrible, so I don't include it like this. But it is a linear formula that you can integrate U by itself, and then integrating B by itself is the same as before with this. So now what is great about this is that they are strong order 2 accurate, and yeah, so that's great. So it's more accurate than the other ones. And what's also great is that even when you are considering discretizations of these type of schemes, it's possible to show some contraction rates, convergence rates in Wasserstein distance towards the stationary distribution that's independent of the dimension, but there is a bias. Okay, so okay, there's certain papers here that have studied convergence rates of such discretization schemes. And okay, so UBU by itself is still not enough. So we need to introduce OHO as well. So OHO is a little bit idealistic scheme because it actually can only work for Gaussians exactly, but that's where we're gonna be using it. So you kind of take away the Hamiltonian part, and then the other parts, the friction and the noise. So, okay, so the idea of OHO is that you move along this part for time step h/2, then you solve the Hamiltonian equations exactly until time step h, and then you again do the O step. So what's nice about this is that both the O step and the H step keep the target distribution invariant. So this scheme has no bias. Okay, so the weak order is infinity, but in terms of strong order, is strong order 1. It's not doing exactly the same dynamics as the original SD would do, but it doesn't have any bias. So the only issue is that you can't really solve this exactly, except for Gaussians. But well, for Gaussians, it's not a problem because this is a linear system, so you can take the matrix exponential and it can be solved exactly. So, all right. So now, in terms of the usual way of doing MCMC, now, because of the bias from these discretizations, typically one uses a Metropolis-Hastings accept-reject step, so you will converge to the correct stationary distribution. So examples are Mala, HMC, randomized HMC. So now the challenge with this is that in order to keep the acceptance rate from collapsing to 0, you need to scale the step size in dimension. So there has been many papers on this. So for Mala, the scaling seems to be like d to the -1/2. for HMC also d to the minus 1/2. For when you randomize the number of leapfrog steps, then actually there is some papers that suggest that d to the minus 1/4 is the right scaling. And again, this has been in particular shown for Gaussian targets that this is the right scaling. So, but in all of these cases, there's still dimension dependency clearly. So now we're gonna use a different idea of creating unbiased estimators using these multi-level methods that has been initiated by Mike Jarrett and several others. So, and this particular idea of using multi-level methods for kinetic Langevin SD has already appeared in the paper by Hamza and AJ and Neil in 2022, where they consider the Euler-Maruyama discretization of kinetic Langevin with these step sizes, and you kind of form telescopic sum to estimate the expectation, where you have a term from the largest step size to the coarsest level of discretization, and then you know, the sum of the differences between levels. And now the challenge is that in order to get unbiased estimator of each of these levels, you already need to couple two chains to remove the initialization bias. And so in the end, to get an unbiased estimator from this difference, you would need to couple 4 chains, and it's not the simplest coupling. Yeah. So instead of that type of estimate, we use a different one. So yeah, it's a very simple one, like Alexis. And there's basically the idea is that none of these are unbiased with respect to the with respect to the station distribution, but the burning lengths increase, and in the limit they become unbiased. So let me just show this figure that makes it clearer. So you start with okay, and copies of this sort of Markov chain with step size H0 and burning B0. So that's level 0. And then you, at level 1, you have like additional B burning steps in terms of like in terms of like you know, diffusion time. So at level 1, the step size is half of the level 0. And level 2, the step size is half of level 1, etc. And the overall burning length, when you look at it, the diffusion time is increasing. So in the end, the bias due to the burning disappears. And so that's the idea of this telescopic scan. And in order to so this was already proposed in a some similar idea was proposed by Costas and Giles in 2020, but didn't make it fully unbiased because they didn't remove the burning bias. They didn't go all the way to infinity in terms of this telescopic sum. So now when we consider estimators of this quantity, we need to make them have a variance that as small as possible. So the idea is that we're gonna get samples from couplings of level 0 and 1, level 1 and 2, etc., that are driven by the same underlying Brownian motion. So they are going to be synchronous couplings. And in this way, their variance is going to be smaller. So at level 0, all you do is initiate from some initial distribution, take B0 plus K steps, and you just take an empirical average of the K steps after the burn-in period. And then you take capital N copies of this. So it's each of them have length K, and you run them capital N times in parallel. So, and then for L bigger than or equal to 0, now you do a coupling of 2 chains, one of them with burning BL, the other one with burning BL plus 1, and they're just each of them have discretization with step HL and step HL plus 1. And they are all driven by the same Brownian motion. And then you consider the differences in this way. So basically, I only compute the values at these dark points here. It's always computed at the same time point in the diffusion time. So these parts are just forgotten, and the differences are always computed at the same position in diffusion time. And now, okay, so the estimator of this difference in between the levels is just you take L plus 1 copies, and you take the average, and then you divide by the expected value of. So this will have be an unbiased estimator of this difference. And now the idea here is that we're going to be using less and less parallel runs between these couplings when the levels level L is increasing, and there will be like the number of phi, and up to the point where the expected value is less than 1/2. After that, you are just including them with this probability. So the idea is that the maximum number of levels you have to go to is random, but with very high probability, it's not going to be large because this probability of inclusion is decreasing geometric rate. So in the end, it is still with a high probability going to be log n. And now, in order for this kind of estimator to have a finite variance and unbiased, there will be some conditions on the variance and expectation of the square of these difference terms. So DLL plus 1 is just the difference between the two coupled chains. And so we need to have this sort of decay at a rate that is faster than 2. And we also have to assume that the cost is of this form, so it's basically proportional to the number of steps. So it's the number of, which is essentially trivially true in our case. So now, assuming that that this expectation of the square of DLL plus 1 is decreasing sufficiently fast, when you define this sum, it will be an unbiased estimator of the target expectation. Variance can be upper bounded in this form. So this would be psi d over psi over psi d, and there is actually central limit theorem that holds. So actually, this estimator satisfies the CLT, and the CLT asymptotic variance can be described as a sum of the variances of these times this term. So the idea is that the variance of this quantity is decreasing at a faster rate, psi d, then you are decreasing the number of samples. So in the end, it's still going to add up to a finite variance. And now this figure will kind of illustrate the idea here. So you have sample parts here of the U-BOO that are basically taking the maximum step size for stability. So it's just a Gaussian target, a one-dimensional Gaussian target. And h equals to 1.5 is roughly at the stability threshold. If you increase it further, it will blow up. And then you look at half of that. And already the two parts, when they are driven by the same Brownian motion, they stay pretty close. And if you decrease it even further by 1/2, then they're almost indistinguishable. So the differences really decrease at order h², which is strong order 2. And that's clearly visible here. So you will be able to, so you can expect that for U-BOO, for a nice distribution, the variance of this difference will be h⁴. And so you satisfy the conditions needed. So now, let's see. So yeah, exactly what I mentioned. So this strong order 2, you have the expectation to be h⁴. And now I'm gonna state some theoretical result under like nice assumptions on the potential. So you assume that it's only convex and smooth. And I also assume that the test function is Lipschitz. And now, in terms of the third derivative, there is this very simple norm that's introduced by Yuan-Su Chen and Kashmiri in 2013. So it's somehow, you have to control the third derivative of the potential in order to get this strong rate of convergence 2 for U-BOO, and also it's can be written in terms of the pages of this three-dimensional tensor. So somehow you look at you fix the first coordinate at I, and you compute this norm, and we have to assume that it's bounded by a constant m. So, all right, this looks a little bit fishy, but if you have like a product distribution, then all this gonna go down to is the maximum of the third derivative amongst all components. So it still like doesn't necessarily have an inherent dimension dependency in terms of this assumption. So now, what we have shown is that assuming the previous 4 assumptions and not too poor initialization, like the maximum minimizer of U that would satisfy this with some mild conditions on the burn-in steps, you have this sort of bound on the asymptotic variance. So again, this CLT, it's a little bit different from the usual CLT in MCMC because it's not the number of steps that tends to infinity, but the number of parallel chains that tends to infinity. And okay, but the asymptotic variance satisfies this, and it's still like decreasing proportionate to the number of steps per chain K, which is a good thing. And there's this term d times h0 to the fourth. So when you set h0 to the t to the minus 1 over fourth, basically you get this sort of bound. So according to this bound, the overall number of gradient evaluations per effective sample is d to the 1 over fourth, which is somewhat similar to what we see with HMC, but in practice, we didn't see this dimension dependency. I'm going to show you simulation results later. And there is some understanding that we build on why that behavior happens in the case of product distribution. So if you have a product distribution and you just look at the single component, which doesn't necessarily have to be in the same coordinate system, but it's a scalar product of an arbitrary unit vector with x, then the asymptotic variance doesn't have any dimension dependency, and the initial step size can be chosen again dimension independently. So there's no dimension dependency here. And the reason is that in this case, for the dynamics itself, each component that's independent evolves independently through every step of the process. So it's just, while in the usual, for example, in HMC, the accept reject step introduces a dependency between different components, and that's why you need to limit your maximum step size to that acceptance rate from collapsing. And we got a similar result for more general functions of multiple projections. Now, I'm going to move on to the more interesting thing is basically, so far I've been talking about stochastic, so far I've been only using full gradients, but what's even more interesting is that you can get the same type of unbiasing when your gradients are not computed exactly, but only you have an unbiased estimator of them here, or not even an unbiased, but another estimator. So there's this SVRG scheme that some of you might have seen, that what it does is, you only compute a full gradient every tau iterations, and that will be in position x hat. And then when you are not in that particular iteration, you estimate the gradient based on that quantity, the full gradient that you computed most recently, plus the differences in this unbiased way. Another possibility is just to use like a full gradient every tau steps, and then you correct with it based on the Hessian at the minimizer. So you just use a quadratic approximation based on the Hessian at the minimizer. So this is the approximate gradient scheme. And yeah, this is a nice place where I have to combine OHO with UBU. So there's the idea in both of these algorithms is that they're going to be most useful in situations where you have many observations and the target is pretty close to Gaussian. So in level 0, you're going to be just using a Gaussian approximation of the potential and then instead of running this UBU, you just take IID Gaussian samples. Then, all right, but you still need to have a diffusion. You still need to have a discretization to couple level 0 and 1. So in level 0, in this coupling, you use the OHO, which is unbiased. So this is still unbiased estimate of the Gaussian approximation. Then in level 1, you use the U-BU, but driven by the same noise as here. And after that, in higher levels, you again make these two pretty close by starting with OHO for the first batch, and this keeps the Gaussian invariant. All of these are always initiated at the Gaussian approximation. And then these two will be pretty close at this point because they are running with the same Brownian motion. And yeah, after that, you run the U-BU. All right, so there's some assumptions on in the stochastic gradient scheme that we kind of update these terms UI such that they are subtract their Hessian at the minimizer, and so they have mean 0 and Hessian 0 at the minimizer, and we use these sort of SVRG stochastic gradients. Now, together with this simple coupling, yeah, and then we have shown that under suitable choices of the initial step size and number of copies, number of parallel copies at each level, we can achieve an asymptotic variance of this form. So what's interesting is that the asymptotic variance of one sample from that target is, for a Lipschitz function, is order 1 over ND already. And we're going to just use order 1 data term evaluation, like gradient UI per effective sample. Whereas if you would use full gradients, you would be using order ND. So that's pretty good improvement. And you can choose the number of iterations at which you compute a full gradient to be an order ND. So only compute after every ND step. So ND is the number of terms UI. And basically, we can just get a very efficient algorithm in this way. And essentially, the same type of situation happens when you use these approximate gradients, where you are just computing the correction of the gradient with this Hessian at the minimizer. And yeah, the number of gradient variation per effective sample is 1. So, I mean, it's a bit surprising that you can do this, but the idea is that if your target is already pretty close to a Gaussian, and the difference here in terms of Wasserstein distance is 1 over square root of n and d times 1 over square root of nd. So the width here is 1 over square root of nd. So at level 0, I am just sampling from the Gaussian this part, and the only thing I actually have to spend gradient evaluations on is estimating the difference here, but the variance of this term is 1 over nd times smaller than the variance of this term. So I need to only take a sample here, nd times less often than I would need to take a sample from this to get the same variance. So that's the underlying idea. Why can we get away with this? And all right, so now finally I get to the simulations. So this is the dimension dependency for a Gaussian target with eigenvalues from 1 to kappa And so you can see that RHMC scales like d to the 1/4, where U is sort of constant. And what I look at is the effective sample sizes in all components and what's the worst one, the maximum, so where it's mixing the slowest. Now, the same behavior holds with different condition number. And we also tested the nonlinear function and norm. And again, you can see that RHMC is d to the 1/4. U is basically constant in dimension. There's no dimension dependency. And with the data condition number is the same. Now, we have tried this MNest. Okay, it's only being used by mathematicians these days, but anyway, it's still not trivial to get MCMC running on it because it's like, yeah, it's around 200 megabytes. So we use multinomial regression. And with the Gaussian prior, so this has all the nice properties that we want, is strongly convex and smooth. And now, the first case, we didn't use any preconditioning. So actually, there was a bit of improvement in U. It's a very sort of particular eigenvalue structure, so it's not as large as you would think, but the dimension is also not huge, it's around 8,000. Now, if you use stochastic gradients, you can do a lot better. All right, so there's an improvement in efficiency. If you use, okay, this is the eigenvalues. So there's basically some eigenvalues that are very large. And for this reason, HMC is not doing too badly. Now, if you do some preconditioning, then actually it's possible to do a lot better. And here with this approximate version, where you just use a hash to correct the gradient, you can get like 0.25 gradient evaluation per effective sample. So that's less than 1 gradient per effective sample. And yeah, so there's a big improvement here compared to the HMC. And finally, yes, I mean, we also tested the test functions as like prediction on the test data set. So that type of test functions, we also see the same improvements. Now, finally, this is like most related to filtering. So you try a Poisson random effect model for soccer scores. So you just have like every week, there's a attacking and defending strength for each team in the Premier League. And we assume that they are kind of connected with a random walk type Gaussian prior. So you could do a particle filter on this, but what we are interested in is, modeling the number of goals. And there's like a Poisson model with a certain link function that we use. And what we are interested in is sampling from the distribution of the wall paths. So it's like a smoothing problem in filtering. But the challenge is that if you consider like, okay, this is the wall prior, and overall there were like 90,000 dimensions, and the condition number is around 40,000. So it's not very trivial to sample from this distribution. And anyway, these are the results. So when you, if you would try HMC, it would take like 1,600 samples per gradients per ESS. But with this approximate version, you get 0.8. So it's around 2,000 times improvement in terms of gradient evaluation. So you're still using the Hessian here, but the matrix vector products are usually much more efficiently computable than full gradient. So there's an improvement. And yeah, so we have shown that this UBUBU is quite competitive with HMC for sampling from stationary distributions. And you can further improve by using stochastic and approximate gradients. Yeah, thank you very much.
Questions or comments?
I'm sorry, I think I misunderstood something because each level is more expensive than the previous one, right?
Yes.
And at some point, your estimates